Morning, eighth graders. It is March 20th. I'm recording this video. I actually, excuse me, recorded this video yesterday, and it took about an hour, if I remember right. And then it didn't save, so I'm doing it for the second time. As you guys are well aware, I am not very tech savvy, so getting used to this whole making videos thing is new to me. So if it seems a little wonky, well, that's because it probably is. Anyways, let's get started. We are starting chapter 16, and it is about the Earth's oceans. We've talked about the oceans before and how the oceans affect the climate. We obviously live on the blue planet, and that's because most of our planet is covered with water. We'll get to the details of that in just a second. 16.1 is about composition and structure of the Earth's oceans. Composition kind of means like what it's made of. What kind of stuff would we find if we took a scoop of water out of the ocean and analyzed it? What kind of stuff is in there? And it's not the same, it's not exactly the same all around the entire Earth. The composition changes depending on where the water is located. Also, we'll talk a little bit about the structure of the Earth's ocean, or rather the structure or the topography underneath the Earth's ocean. All right, here we go. We've talked about this lots of times before. You probably recall 70% of the Earth's surface is covered with water, and that water on the entire planet, of all of the water on the entire planet, 97% of it is salt water. Okay, so that's the oceans. Obviously, there's some saltwater lakes and things like that around the world, but that's a teeny tiny amount in comparison to the size of the entire ocean. Now, when we think about the ocean, or oceans, I should say, there are 5 oceans. The Pacific and the Atlantic, those are the two that we're probably the most familiar with because we find those, they border our continent. Anyways, so the Pacific is the largest and the deepest. If you recall, the deepest spot, or the deepest location on Earth would be the Marianas Trench. It's about 7 miles deep. We'll talk about that in a little bit. And then on the other, so here's the Pacific is to the west of North America. And then on the east side of North America is the Atlantic. The Atlantic Ocean is about half of the size of the Pacific Ocean. The next is the Indian Ocean. Indian Ocean's kind of between Africa and Australia and just south of India. And then we have the Middle East over here. And we'll talk about, when we talk about composition of salt in the water, we'll talk more specifically about this area because I have some personal experience. The next one is the Southern Ocean, and they call it the Southern Ocean because guess what? It's down south. It is surrounding Antarctica. It's a very cold ocean, and it's covered. Parts of it are covered by ice all year round. It doesn't melt because the sun's rays never have enough energy to heat up the ground, the earth, the snow, whatever it is, enough so that it actually melts. And then on the opposite side, in the North Pole, we have the Arctic Ocean, and much of the Arctic Ocean is frozen as well. So when we think about all the water on our planet, there's a really huge, almost mind-boggling amount of water on our ocean, or in our oceans. And so we kind of think about where it came from. The problem here is that we don't really know because guess what? It comes as no surprise. We weren't here, so we don't know exactly how it formed. However, scientists think they kind of have it figured out, although there's a couple of different ideas. The main scientific explanation as to how the water got here on our planet was that volcanic eruptions put large amounts of water vapor into the atmosphere. And those water vapors eventually started condense and formed droplets. Those droplets fell down and it rained for a really long time. We'll get to that in a second. Think about when the Earth was relatively new. Okay, when I say relatively, like the difference of several million years is kind of like, it doesn't make much of a difference when we're talking about the history of the Earth. So over 4 billion years ago, the Earth was essentially a really hot molten planet that had a thin crust around it because that rocky material that formed as a result of the magma cooling, I guess I should say, created a crust, and then underneath that crust there was a lot of volcanic activity. So volcanoes essentially were just probably just about everywhere, um, and all of that outgassing, the water vapors were able to get out, and they condense in the atmosphere. And we know that when water vapors condense, they form droplets, and droplets form precipitation, and that precipitation makes rain. It rained for a really long time, probably about 10,000 years. And what that did then was it filled all of the low-lying areas, or what we call basins. Um, all of the low-lying areas got filled up with water. Pretty straightforward, right? We understand that, we can watch it rain and we see the water, rolling down the street, or uh, flowing into a river, or whatever it happens to be. So oceans, lakes, rivers, streams, underground aquifers, all that stuff kind of filled up. When we think about Pangea, back in the Permian, so we're talking 225 million years ago. Pangea was that supercontinent, and as the tectonic plates started moving, it started opening up areas inland, and it was creating inland seas. And so as the Earth is sort of reforming, um, it will, or it was, opening new areas and creating new oceans in the meantime. Okay, so the older oceans, they disappeared, or rather changed, and new oceans formed, and we currently now have 5 oceans like we just talked about. So when we think about the composition of the seawater, um, we think about what the seawater is actually made of. Okay, what's in there? If we take a scoop of seawater, what are we going to find? What we find is that the water, and we think about rain. Does rain have salt in it? Well, of course it doesn't. We've all been outside in a rainstorm and we've tasted the water. I'm sure at some point in time, we've tasted the water that came from a raindrop, and we know that that doesn't have salt in it. Well, as the rain falls, it flows over the land and it can melt minerals that we call salt. And some of those minerals would be chloride, sodium, magnesium, sulfur, calcium. But more importantly, we think about the oceans, we think about sodium and chlorine as they are bonded together. Okay, so that makes sodium chloride, and sodium chloride is table salt. All right, so rain is falling, and we know that if we take a tablespoon of salt and we put it into a glass of water, what happens to the salt? It dissolves away, right? Well, the same thing happened in the oceans. When it rained, the water fell down and it was able to dissolve those minerals. And mainly the one we're thinking about is the salt. Okay, there are other ones that also are forming as well, but we're mainly concerned with the salt, right? So rivers and streams are draining water that's falling as precipitation, rain, sleet, snow, whatever it happens to be, and it's making its way to the ocean. And as it's on its way, it's dissolving minerals, and that's where the salt comes from. We also get some minerals from volcanic or tectonic activity in the bottom of the ocean, like hydrothermal vents that are, they're expelling sulfur gases and things like that into the ocean. Way down deep. We're thinking like deep ocean trenches, like the Marianas Trench. So we think about, look at the graph here, and you guys know I like looking at graphs because you can get a lot of information very quickly. Most of the salt that's dissolved, or the salts that are dissolved in the ocean, are chlorine, because chlorine's a relatively big atom compared to sodium. And then sodium is 31%. And then we have these other, magnesium, sulfur, and then these small amounts of calcium. Okay, so when we think about salt in the ocean, we think about a term called salinity. Salinity is the measure of all of the salts that are dissolved in the water. Okay, it doesn't matter if we're taking a cup of water and we're adding salt to it, that has a particular salinity, which is the measure of the mass of the dissolved solid. So the mass of the salt that's dissolved in the mass of water. Okay, so seawater is roughly 35 parts per thousand. Okay, so every 1,000 grams of seawater would have 35 grams of salt dissolved in it. Now, around the Earth, there are different amounts of salinity, or the salinity changes, and those changes are based on a couple of different things. Okay, We'll get into some details about that in a little bit, but the main idea here is that warm water will hold more salt molecules, or salt ions, I guess I should say, because they're not molecules, they're ions, will hold more salt ions than cold water. So I think about this, and I mentioned earlier about the Middle East here. When I was deployed overseas, we spent some time in the Persian Gulf, and we had some liberty when we were in Bahrain, and we went scuba diving. That was great. We love scuba diving, right? Well, the problem is that the Persian Gulf, the water is so warm. It was like 92 or 93 degrees, something like that. The water is so warm that the amount of salt that's dissolved in the water makes it really uncomfortable if you get it in your eyes. The other thing is that there are not very many organisms that can survive very well in water that has that high of salinity. So we went scuba diving, and there really was nothing to see. And it wasn't very deep, and the water was really warm. It was actually tremendously boring, but it was kind of fun to say that I've been scuba diving in the Persian Gulf. Anyways, we can look at the infographic here, and notice when we go to the poles, right? So the North or the South Pole, the salinity decreases, okay? So we look over here, and this is in the Bering Sea. You can see here, I know it's kind of fuzzy. In the Bering Sea, the salinity is about 32 degrees. Or, sorry, 32 degrees. The salinity is measured at 32, okay? If you go to areas where the water tends to be warmer, you'll see that that salinity increases, okay? So 37.5 out here in the Atlantic Ocean. This is obviously closer near the equator. Also, we go over here, and this is the Indian Ocean, has a salinity of 36, which is definitely warmer. I'm not exactly sure what the salinity of the Persian Gulf is, or the water in the Persian Gulf. I believe it's probably quite a bit higher than 36. Probably I'll look that up a little bit later, just so I can get a better idea. Anyways, not all seawater is uniform in its salinity. So we think about things like where a river meets the ocean, okay? In that area, we have fresh water from a river is mixing with salt water in the ocean, and we call that water brackish, okay? In that brackish water, it's usually around the mouth of the river, and it can range anywhere from 1 to about 17 parts per thousand. Obviously, we have, if you think about it like we're thinning out the water a little bit, we're thinning out the salt water, I guess, by adding fresh water to it. Now, interestingly, in brackish water, there are some organisms that can thrive there. They do very well. A lot of organisms cannot. We think about bull sharks, for example. Bull sharks are adapted to be able to be in both freshwater and saltwater. We usually think of sharks as, being a marine organism, so a saltwater organism, but they can go into freshwater. In fact, bull sharks have been spotted as far north up the Mississippi River as Illinois. And, that's like 700 miles up the river. So it's, sort of an interesting thing to think about, sharks that could be both in freshwater or in saltwater. Now, when we increase the salinity, and we think about it like we have water molecules, and then interspersed with all the water molecules are these salt molecules. And what that does is it increases the density of the water, okay? So if I were to take a cup of just regular fresh water and compare it to a cup of salt water, the salt water is going to weigh more, even though the volume of both of those is going to be the same. The salt water will weigh more because it has ions of salt that are dissolved in the water, and that makes it more dense, and therefore things become more buoyant, or if they are less dense than the water, they'll have a higher tendency to float, okay? So that's buoyancy, right? Now, getting to the geography or the topography on the ocean floor, things that we see on land, we also see underwater. There are underwater mountain ranges and plains and plateaus. In fact, the largest mountain on Earth is actually underwater. Now, I know if I were to ask you, hey, what's the largest mountain on Earth?
Meeting in Mr. Dunham's room.
you probably would say,
Must be for all of you.
if I said the largest, where's the largest mountain on Earth? I'm sure most of you would probably say, oh, that's Mount Everest. That's an easy one. But it's actually not. It's a mountain that's underwater, and it's part of the Hawaiian island chain. I'm going to try and pick up the pace here a little bit because apparently I have a meeting. Now, when we think about the area near the coastline or near the continent, we call those the continental margins, okay? That's the part of the ocean basin that's right next to the continent. So we look at this area here. This is the continental margin. If I'm going fast, feel free to pause the video so you have time to get the notes and look at the diagram. The abyssal plain then are these large flat areas of the sea floor that extends way out into the ocean here. So, you know, we have these coastal regions. It's typically more shallow. We'll get into the details of sunlight and how much sun can penetrate and things like that. But the abyssal plain, that's sort of like what we think of when we think of like the open ocean, okay? Those are the deepest parts of the bottom of the ocean. And we've talked a lot about mid-ocean ridges in the past. When we have tectonic plates that are diverging, okay, now remember, diverging means they're going apart from one another. As we have that divergence happening, it opens up these areas where it's easy for magma to come up to the surface. When that magma comes up to the surface, it creates these underwater ridges. We recall learning many chapters ago about magnetic reversals. The basalt, which is an iron-rich mineral, changes direction based on the poles or the magnetic poles of the earth. And when those magnetic poles have reversed in the past, it changes the alignment or the direction that those basalt minerals align themselves. This is also what forms underwater volcanic mountains. Ocean trenches, I'm going to pause it here for a minute and go to this meeting, and I'll be back with you guys in just a little bit. Okay, I'm back. Sorry about that. As it turns out, they are having a meeting right now about Zoom, which is the program that I'm using right now to show you or to record this video for you guys. Okay, so the other thing that we see in the bottom of the ocean are these ocean trenches. Excuse me, we've talked about ocean trenches before and how they form. We're looking at a diagram of the Marianas Trench. That's about 11,000 meters, or just to ballpark it, right around 7 miles. It is about as deep as Mount Everest is tall, okay? And if you guys recall back, what forms these ocean trenches is when we have converging tectonic plates. As they are coming together, one of those tectonic plates is going to be more dense and one is going to be less dense. And maybe we want to think about it as one is more buoyant, okay? I like to use the word floaty, okay? One is a little more floaty than the other, and what ends up happening is as they are coming into contact with each other and pushing, one of them is going to have to subduct or go underneath the other one. Now, I'll get my hand up close here so you can see it a little bit better. So we have these two plates coming together, and as the one is subducting, it's sort of like catching the edge of the other tectonic plate, and it pulls it down. And this is what forms these deep underwater trenches. Okay, so that area between my fingers there on the top side would be what I would call the trench, okay? Obviously, that's probably not the best way to diagram that or to demonstrate that, but it kind of works. So obviously, you know, the ocean is one of the least explored places. It's not one of, it is the least explored place on our planet. You know, we know more about space probably than we do, or have done more exploration in space than we have our own ocean, right? Well, there's some limitations. If you think about the amount of pressure that's created by water, if you've ever jumped in a swimming pool and you've gone down to the bottom, you probably feel your ears are kind of like, they feel like they want to pop a little bit. And a swimming pool, by all rights, is very, very shallow compared to the ocean. Well, the ocean is 7 miles deep. Every 33 feet that we go down in underwater, we are experiencing 1 atmosphere of pressure more than we had been previously. As you're sitting right now watching this video, you have 1 atmosphere of pressure that's pushing on you. You don't really notice it because it's always been pushing on you. Ever since you were born, it's been pushing on you, okay? That's 1 atmosphere of pressure. If you go down underwater 33 feet, you're going to experience another atmosphere of pressure. And about 33 feet after that, another atmosphere of pressure. So consider how many atmospheres of pressure there are when you go down 7 miles. This poses some problems because it's difficult for underwater vehicles to go that deeply. And in order to resist or withstand that amount of intense pressure, we have to have very, very specialized vehicles that will go down that deep. And not very many people have been down at the bottom of the Marianas Trench, or even close for that matter, but it has happened, and we have had scientists that have been there. Okay, so again, you know, like a lot of places on our planet, we have resources, you know, kind of like we might find a gold mine somewhere, right? Well, there are also resources on the bottom of the ocean. The problem is that depending on how deep it is, it's hard to access those things. But there are resources and fossil fuels that we can find in the bottom of the ocean, in the bottom of the Marianas Trench. Sorry, not the bottom of the Marianas Trench, the bottom of the ocean. So one thing that has a big effect on the type of things that can live, or the organisms that can survive in different zones of the ocean, depends on the amount of sunlight. Okay, now I'm going to start down deep. Way down deep in the bottom of the ocean, that's what we call the midnight zone. There's no sunlight that can penetrate that deeply. Okay, organisms that live there have to have some sort of, if they are going to have any vision at all, they have to have some of their own light source. And the first thing that comes to mind, and probably the first thing that comes to your minds, is the anglerfish, right? It has like a fishing pole looking thing that sticks off of its head, and it has some, like a little bioluminescent thing that lights up, and it attracts fish, and then that fish comes by and they eat, you know, so the anglerfish gets to have lunch, right? Other organisms, if they have any type of vision, they have to be able to create their own light. Now, in the middle zone of the ocean, okay, so now we're looking at this area right here. In the middle zone, that's what we call the twilight zone. If you think about twilight at, you know, if we're out and about and the sun goes down, once the sun goes down past the horizon, it's not really dark yet, but there's just not as much light in the atmosphere. Okay, so light waves are coming from the sun, they're bouncing off things in the atmosphere, and they're creating some ambient light, but things start to look kind of gray because there's not enough light reflecting off of objects to be able to see the color very well. So in that middle zone, we have the same thing going on. Everything just kind of looks like a sort of a bluish color, and that's because there's not enough light for us to be reflecting off of objects to be able to see much color. Up in the surface, that's the area that gets the most sunlight. This is where photosynthesis occurs, and being that photosynthesis can happen, then we have algae and other things that can, or photosynthetic organisms that can grow there, and that provides food source. And that is because there are food sources there. That's typically where we find the most life in the ocean, is up near the surface. Obviously, in the coastal regions near the surface, that's where we find the most organisms. When we say near the surface, we're not talking about like just right on the surface, but you know, it could be down anywhere up to like 90 meters, something like that. So the ocean definitely has different layers. If you've ever been to the lake during the summertime, and maybe you were on the pontoon, you jumped off the pontoon and you went down, you notice that after you went down just a few feet, you feel a temperature change, like a significant temperature change. Those are called thermoclines, and they happen in the water sort of stays suspended in different areas because of changes or differences in the density. And those densities, changes or differences in density, are caused because of the salt that's in the water. Okay, so it varies by how deep you're going in the ocean, right? As you go down, the water temperature decreases, and that kind of makes sense, right? Because we're getting further away from the surface where the sun is shining. So it gets colder and colder. And we know that warm water holds more salt than cold water does. So as you go down, the density of the water is less and less, and the water is colder and colder, colder and colder. So we have those differences, and that creates those different layers within the ocean. We're not going to do this pop quiz because you guys aren't here with me. But we can just run through this real quick. What percentage of the Earth's surface is covered by water? 70%, good. Scientists believe it rained for about how long? That's right, 10,000 years. Seawater and water from the sea or ocean that has an average salinity of how many parts per thousand? 35. Good job. And salt water that is mixed with fresh water, we call that brackish. Very good. All right. So that's it for 16.2. I'm not exactly sure how far we're into this, but you can pause at this point or you can continue on if you need to keep going. Okay, 16.2 now is about ocean waves and tides. And one thing to note about tides, we'll talk more about tides when we start talking about the Earth, Sun, and Moon system and how those things interact. But the moon and the sun have a significant effect on the water in the ocean. Okay, so let's take this back down to the basics. All waves have basically the same part. It doesn't matter if we're talking about sound waves, which are compressional or longitudinal waves, or we're talking about mechanical waves, like waves in the like water waves, or maybe electromagnetic waves that come from the sun. They all have a crest, which is the top of the wave, and they all have a trough, which is the bottom of the wave. Now, the wavelength is then the distance from a point on one wave to its counterpoint, so the exact same point on the wave next to it. That's the wavelength. Almost always it gets measured from crest to crest, but you could measure it from trough to trough if you wanted to. If you wanted to measure it from somewhere in the middle of the wave, that would be fine too. But the problem is that it's really difficult to isolate those things, but it's pretty easy to see the crest and the trough, and so we can make those comparisons. So surface waves are waves that are on the top of the water, and they typically are the ones that we notice that roll up onto the beaches, okay? Those waves are caused by wind. When the wind blows, there's friction occurring between the air molecules, okay, and the water molecules. Now, it doesn't seem like there would be a lot of friction there, but when you think about a constant blowing wind, as it's having contact with the surface of the water, it's going to create little ripples. And you can see this picture has little tiny ripples. And if the wind continues to blow, those ripples will then start to get larger and larger and larger, and they'll turn into different sized waves, okay? So the ripples will become larger and larger until we would call them waves. Now, this is a big wave in the ocean. Some things that affect the size of waves we'll get to in a second here. This would be a really unusual wave. This wave probably isn't caused by a tide or a tsunami, which we'll get to in a little bit here. But if the wind is allowed to blow for a long time, right? So we can have little tiny ripples, or we can have these big honking waves that are the ones that can, unfortunately, can get big enough that they can overturn even big, large ships. Okay. The size of a wave depends on three different things. Number one, I'm going to jump ahead here for just a second. Yeah, okay. The wind speed, okay? So how fast the wind is blowing. Obviously, the more wind that's blowing over a spot, the more friction is going to occur between the water molecules in the air, and the larger the waves are going to be, or the more air passes over a point in a given period of time. The time would be how long that wind has been blowing, because maybe it's blowing for a really long time, maybe not that long. But typically when we see these massive, massive waves out in the ocean, it's because the wind has been blowing for a long time over very far distances. Now, distance is the last part. If we think about small lakes, we come from the land of 10,000 lakes, and there are some small lakes and there are some really big lakes. On those really big lakes, we tend to see on a windy day, those waves get really big, okay? If you go to a smaller lake, those waves aren't going to have an opportunity to build really large waves, so we typically have relatively small waves, okay? Now, we think about white caps, right? What causes the caps to get white? Well, air is mixing in with the water. And the reason it's mixing in with the water is because the water isn't able to support the weight of the wave as it's rising up. We'll get to that in just a second here. Okay, one very important thing to keep in mind or to understand is that waves don't transport water from one location to another. Do they move a little bit? Yes, of course they do. They move in a circular kind of a pattern. as we can see here. But generally speaking, waves aren't what's moving the water. It's friction from the air pushing on it that's moving the water, okay? So think about this. You're at the lake, you're sitting on a dock, you throw your bobber out there, okay? You're gonna try and catch a nice crappie or something like that. As you're looking at your bobber, the wind is blowing, but your bobber is just kind of going up and down with the waves, right? Well, yeah, it's going to move, but it's not moving because the water is moving. It's moving because the air that's causing the waves as well, that air is pushing on the bobber and eventually going to move it, right? So pay attention to that next time you're out watching, if you're out bobber fishing, just watch your bobber. It just goes up and down, okay? Now, to the next part. The anatomy or the structure of a wave, as it's coming into the shore, the wavelength decreases, okay? So if we look at the diagram down here, the water is moving into the shore, and as it comes in contact with the bottom or the sea floor or the floor of the lake or the shoreline or whatever however you want to think about it, as it's coming into contact, it's going to slow down. And as it's slowing down because of that friction, it's going to make the wave compress or get shorter, okay? So the wavelength decreases. Well, all of that stuff, the water, has to go somewhere. So as the wave gets decreased or compressed, it has to rise up, okay? So what happens then, if you look at the picture, as it approaches the shoreline, it forces the water up into the air, and at some point the wave itself cannot support the mass of the water, and it comes crashing over a little bit. Now, if this happens out in the middle of the lake, or not even the middle of the lake, but just out in open water, then it creates this whiteness where the air is mixing in with the water. We call those white caps, right? And probably all of us have experienced that at some point. We've looked out at the lake on a windy day and we see those white caps, okay? If it comes all the way into the shore, then we call those breakers. And this is really evident if you ever go somewhere where there's, you know, like you're on the ocean or the coastline and you have these big waves coming in, and maybe there are people there surfing, right? Because this is what makes those surfing waves so great. Now, if you had a surfboard, you wouldn't be able to catch a wave very easily on a wave like out here in the water. But as it approaches the shore and the wave increases in height, you're going to have better chance of gravity pulling you down the edge or the face of the wave. And that's, you know, obviously what makes surfing possible. Okay. One other type of wave is what we call a tsunami. Tsunamis are almost always caused by some large disturbance of the water, like an underwater earthquake or things like that. Now, we've talked before about plates or slabs of earth or rock that come into contact and push against each other. So we call those plate boundaries. And at those plate boundaries, it kind of works the same. One is going to subduct under the other one. Well, when the tension forces get really tight, then eventually the force becomes so great that it breaks free. And when you have a large slab of ocean floor that does this like that, it moves a tremendous amount of water all at the same time, and it creates these large tsunamis. Okay, so oftentimes tsunamis are associated with underground earthquakes. What happens is we have these massive waves that get formed, and they are highly destructive. They'll flow up onto the land. The most destructive one that I can think of that's happened in recent times was probably the one that caused by an underwater earthquake, and the water created this huge wave, and it came ashore in basically all of Japan, but it caused some real damage in Fukushima, Japan, and damaged a nuclear reactor there. And it made pretty big news. Obviously, I'm not surprised you guys probably don't remember that, because you would have been probably, I don't know, I suppose third grade, something like that. Now, wavelength of a regular wave on a lake is relatively short. It could be anywhere from, you know, a centimeter, maybe less than that, probably not, a centimeter to maybe a foot or 2 feet, something like that. Tsunamis are different, okay? If you were to experience a tsunami and you were way out in the ocean, you would have no idea that you were even like your boat was even on a tsunami, because these wavelengths are like hundreds of kilometers long. Okay, I want you to think about something. 100 kilometers, well, let's just, from Ulen to Hitterdal is about 12 kilometers. Okay, so multiply that times about 9, and that's how far 100 kilometers is. So if you drove back and forth from Ulen to Hitterdal, you know, that would give you an idea of the length of the wave. Now, remember, as that wave is approaching the shore and it's getting more and more shallow, that wave length decreases, the wave height increases, and it gets higher and higher and higher, and we end up with these waves that can become very, very tall. You know, out in the middle of the ocean, these really long wavelengths, you might have a wave that is less than 30 centimeters, and I'm just going to try and, okay, from here to here, okay, here to here, that's roughly 30 centimeters, okay, so a little bit more than how big my huge honking head is. All right. All right, now on to tides, different kind of wave. Tides are, actually, they're not really a wave. It's a water that comes ashore. It's the periodic rising and falling of the Earth's, or the water in the ocean, and it's caused by gravity being exerted on the water from the sun and the moon. Okay. Now we know that the moon is passing over us, and it comes, you know, over the ocean. And actually, I'll go to the next picture here. It'll make more sense. Well, maybe not. As the moon passes over, it has enough gravitational pull on the water that it's able to create these bulges of water on the Earth's surface. And as it's passing over the land, it pulls that water up onto the land, or kind of like floods the land. And we have what's called tidal range, which is the next slide here. That's the difference in water level between the low tide and the high tide. Okay, so in low tide, maybe if you park your boat at a place where the tides come in and go out, your boat at one point in time might be sitting on the bottom of the ocean, okay, like here, or when high tide comes in, you're floating up high. So it's not an issue, right? But that range is the difference between high tide and low tide. Okay, there are some things that affect that, and depending on the position of the sun and the moon, it can create really big bulges or these really thin areas where it's going to be low tide. Okay, so the tides are happening because of the gravity that's exerted on the Earth, or the Earth's oceans, from the sun and the moon. Okay, the sun is really far away, 93 million miles. If you were going to drive a car there going 100 miles an hour, it would take you about 103 years to get to the sun. And that's without stopping for gas or potty breaks. Okay. So that's a tremendous amount of gravity. Even though the sun is very far away, it has so much mass that it exerts a lot of gravity. Now, the moon, not nearly as large as the sun, actually nowhere even close, but because it's significantly closer to the Earth, it does have a gravitational pull, or a gravitational effect on the Earth. Okay, so there's a couple different tides that occur. A spring tide is the first one. It is the tide that has the greatest tidal range. Okay, so recall, tidal range is high tide to low tide, and the distance, or how much space or length, or however you want to think about it, you know, water depth, I'm not sure how, just get it in your head somehow. Okay, that has the greatest tidal range, and the reason it does is because as the sun is exerting gravity, the moon is also exerting gravity. Now, in a spring tide, the sun, the Earth, and the moon are all in line with one another. Okay, and what that does is it creates these areas on the 90 degrees away from that straight line, these areas where the ocean is going to get pulled kind of thin, and near the shoreline you're going to be able to see that and detect it very easily. Okay, what it also does is it creates a very high tide in those areas where the gravitational force is the greatest. Okay, so gravitational force is the greatest in line and the lowest at the 90-degree angles. Okay, so low tide, high tide. If we think about now there's also, maybe this is a better diagram. We have the sun. Obviously, we only have one moon. It's just showing different locations, but the effect is kind of the same. If it's pulling the Earth's ocean. Now, creating these bulges, and those bulges are going to increase the depth of the ocean in those areas. Okay. Now, the next one, and this is a good picture too, but I'll go ahead a slide, is called a neap tide. This is the lowest tidal range. It occurs or happens when the sun and the moon and the earth form a 90-degree angle from one another, okay? So sun, earth, moon, and we can look at the diagram here. And this is where we have the lowest tidal range because the gravitational pull has to get shared with a couple different directions, okay? If you want to think of it as one pulls to the left, one pulls up. I mean, obviously, if you're in space, there's no left and there's no up, but that's how that's working, okay? So we have a low tidal range during a neap tide. You're going to have to remember 90-degree angle. That's a neap tide. Spring tide, they're all in line with one another. Okay, that's it for 16.2. If you're watching this all the way through, we'll continue on. If not, you can go ahead and pause your video there. All right, 16.3 is about ocean currents. We've talked about ocean currents a lot in the past, especially when we talked about the Earth's atmosphere and how trade winds blow around the Earth and things like that. Well, those things have an effect and they create ocean current, okay? So ocean current, huge, massive volumes of water flowing in a certain direction. Okay, that's an ocean current. There was a big storm. If you look at this picture here, it'll help. There was a big storm that happened back in 1990. Okay, and a container ship ended up having a bunch of the containers that broke off and fell into the ocean. Okay, that happened in 1990, in May of 1990. Okay. In 1991, around New Year's, those tennis shoes, Nike tennis shoes, started washing up on the shoreline in the Pacific Northwest, okay? Obviously, we've known about ocean currents for a long, long time, but this is just kind of a fun way to sort of see it in action, right? Because one drop of water is going to look the same as another drop of water. Unless we see something floating and moving from one place to another, it's hard for us to really get a visual of that or get an idea of that in our head, okay? So 1991, New Year's, is when they started finding all these shoes, these Nike shoes washing up on the shoreline, okay? And then they found in the summer of 1992, they started finding these tennis shoes washing up on the shores in Hawaii. Okay, well, kind of a fun little thing. Okay, so surface currents in the ocean are caused by wind. Obviously, we know about trade winds, and those trade winds are blowing water because of friction from one place to another. And these surface currents help to carry warm water or cold water, depending on whether the water is flowing from the equator up to northern latitudes or from the northern latitudes back down to the equator. They can extend down below the surface of the water up to 400 meters, okay? So quite a ways, and it's not like wind is blowing down there, but the constant motion on the surface creates water that's moving all in the same direction very, very deeply. And depending on how fast the wind is blowing or the wind speed, the water can move up to 100 kilometers in a day. Again, 100 kilometers, think about how far it is from Ulen to Hitterdal. It's about 12 kilometers. So imagine driving back and forth. I'll give you an idea of how far that is. Okay, so we've talked before about prevailing winds. Those are trade winds that on the eastern side of North America, they're coming from Africa, blowing to the east. And if you're on the western side of North America, or North or South America for that matter, it's blowing from east to west, okay? Those are obviously hugely important for sailboats back in the day. Now, obviously, most boats are powered by motors that create propulsion, but the propulsion prior to that would have been from a sail or the wind blowing on the sail. So those were really, really important, obviously. Okay. Other things that occur are what we call a gyre, or this looped system where we have water that flows up into the northern latitudes from the equator. So we have warm water near the equator that flows around. Obviously, water doesn't flow through a continent, so it hits the continent and it gets forced to go somewhere. So it gets pushed up into the northern areas, so up in near the Bering Sea, and then it's cooled off, obviously, because it's quite a bit colder in the ocean up there. The climate is colder than it is down now by the equator. And so we have cold water now coming back down by the equator, and it gets warmed up because it's near the equator. The sun's rays are more direct there, and so it warms up more easily, warms up, and it flows back up to the north. And we have these circulation patterns that are happening all around the earth. Okay, every one of our oceans has these big circulation patterns. Well, those are really important because they help to mix the water. Otherwise, the water near the ocean would end up getting really, really, really warm, and the water up in the polar regions would be significantly cooler. Okay. Now, we've talked about the Coriolis effect before. That's the effect or the movement of wind and water. If you're in the northern hemisphere, that stuff it spins to the right. If you're in the southern hemisphere, it spins to the left, and that's caused by the Earth rotating on its axis. And we've talked about that before. So other things that have effect on ocean currents are the topography or where the land is. Obviously, we know that water can't flow through a continent very well or at all unless there are passageways. So we look like in between islands and things like that, or here, this one is pretty easy to see. We have water from the ocean that flows around Cuba into the Gulf of Mexico, around the southern tip of Florida, and then back up into the main body of the Atlantic Ocean. Up into the northern latitudes, it'll flow up around Greenland and Iceland and probably the Scandinavian countries, and then work its way down past the western side of Europe and near the equator and circulate back around again. It will keep making this loop. As the water gets forced through these areas, right? So think about this. We have water pushing on water, and it's going to force it through those areas. And so when you get to areas between islands or land masses, the water is going to start to flow faster. So you're going to have an increase in the speed of the current in those areas. Now, one important thing that happens is what we call upwelling. This diagram, or this is kind of hard to see. Or rather to tell where the land is. But this green area here is like what would be the land, okay? And then the coastal range is the area underwater or the underwater shoreline. What happens is as water is being pushed by wind, okay, remember friction from the wind is pushing on the water. And as it's doing that, it's pushing this water out of the way, right? So it's pushing it that way. Well, the water then, because it's getting pushed out of the way, water from down below gets pulled up to the surface to take the place or the space that's left behind from that water. Now, it's not like there's an empty space here, but the water gets pushed out, and immediately as it's getting pushed out, more water comes up from the bottom. This is really important because at the bottom is where we have a lot of nutrients. I mean, think about all of the little things in the ocean that die and decay away, and all of that nutrient, it turns into nutrient, settles down to the bottom of the ocean. Well, this upwelling near coastlines is what helps to keep those nutrients in a cycle so they can come up to the surface. And it works out really well for those photosynthetic organisms because it provides a nutrient source so those things can grow. So because of that, we have nutrient-rich water, so we have algae that can grow, and we have food source for things like small fish, and then small fish get eaten by the bigger fish, and then that creates a really nice food web for all of the organisms that live there, because depending on if you're going to eat the algae or you're going to be the big shark that eats the fish or whatever it happens to be. Okay, so it's really important for ecosystems to have this occurring. It also occurs in our lakes around here. We've talked about this before. When we have the water that turns over in the fall and in the spring, or when the snow and ice melts, we have turnover of the lake, and it mixes all of that nutrient-rich water from the bottom of the ocean and flips it around to the top, so that we have photosynthetic organisms that can start to proliferate. And because they're proliferating, that's a food source for smaller fish, and you can see how it goes from there. Okay, other things that cause currents are density currents. And think about water from the surface of the ocean changes because of the density of the water. Okay. Now, things that would change the density of the water would be the temperature or the fact that there is salt in the water. And we think about, um, think about areas where we have polar ice sheets, and those ice sheets are glaciers. No, it's not. We're not really talking about glaciers. We're more talking about ice sheets. Glaciers tend to be on mountains. I mean, obviously that water melts and then it flows to a larger body of water. If we think about an ice sheet as it's melting, it's like putting ice in a glass of warm pop. It's going to thin out the pop, and the pop is going to become what we call watery. Well, when we have salt water being thinned out by melting ice, and that melting ice does, or I'm sorry, the melting ice does not have salt in it. Okay. When seawater freezes, the salt is left behind in the liquid water. And so if we were to go and take a chunk of a glacier, or sorry, an ice sheet, it's not going to have salt in it like fresh, or like the salt water, the liquid water does. Okay. Well, it thins it out and it changes the density of the water because we're thinning out the salt. And when we do that, it also changes the current. We talked about gyres. Gyres also are responsible for transferring energy. And when we think about transferring energy, we're talking about maybe some kinetic energy because the water is in motion, it's moving around. But we think about thermal energy because the water near the equator is going to heat up more than the water in the polar regions. Okay, so because the sun's rays hit more directly, the water there becomes warmer and it gets circulated up into those northern and southern latitudes and transfers thermal energy, or if you want to think about it like this, it heats up those areas. Okay. Warm water, depending on where you're at, and we, take it back to like, think about the United States. If you are near a coastline, the water there is relatively cool, right? Because the water is coming, if you're on the West Coast, the water is coming from the northern latitudes, so it's pretty cold. Okay. If you're like, say you're in Florida and you want to go snorkeling, the water is pretty warm. And that's because the water is coming more directly from the equator. It hasn't made its way up to the polar regions where it's going to cool off. Okay. So in doing this, these gyres or these ocean currents are transferring thermal energy all around the planet. Okay. This is what we're looking at, the Gulf of Mexico here. There's a loop, the water near the equator gets pushed up through here, around, creates this nice warm area where people like to go and hang out on the beach, and then eventually makes its way up towards the northeastern seaboard, and eventually will make its way up to the north and around over to the Scandinavian countries. We call this whole thing the Great Ocean Conveyor Belt. Okay. It is transferring water that's warmed up near the equator up to the northern latitudes where it cools off, and then it flows back down to the equator where it gets warmed up again, or even to the southern latitudes, like to the Southern Ocean. The cycle that it takes, I mean, you're thinking about water, if we could trace or follow one drop of water, that entire path, it could take upwards of 1,000 years. Now, obviously, has anybody really ever done that? Probably not. This is an estimate done by scientific modeling. So one other thing that happens, and this is because of these gyres, is we have what's forming, or what we know as the Great Pacific Garbage Patch. Now, there are garbage patches, not just in the Pacific, but this is what it looks like. There was a guy that was sailing his boat, and all of a sudden, he was out in the, well, not all of a sudden, he was in the middle of the ocean, and then all of a sudden, he comes upon like this huge, what looked like a landfill in the middle of the ocean. Well, he couldn't figure out where, I mean, obviously, we know where it's coming from, right? Humans. Because the fish obviously aren't littering like that. But the gyres, or the way that the water circulates around in the ocean, has created this situation where it's collecting all of the trash that ends up in the water from the western coast of North America and the eastern coast of the Asian continent. So there's two garbage patches. There's the eastern garbage patch, and then there's the western garbage patch. And then we have this area in the middle where there's sort of trash that's sort of just kind of mixed in. Now, this garbage and this trash, it's not like it's just sitting on the surface, guys. This stuff is going down several meters underneath the ocean. Okay, if you take a scoop of water and analyze or take a good look at what's in that water, here's a picture of the gyres. We see the circulation pattern. We see all of these little micro or these plastics, right? Now, those are relatively big chunks of plastic, and as you can see, organisms are consuming that stuff because it looks like something they want to eat, right? Maybe we've been fishing and you pick a different color lure because you think it may be that the fish will see it better or it looks more appetizing or whatever. Well, guess what? Organisms in the ocean, they see colorful stuff and they want to eat it. So we have all these organisms eating all of this material, and it ends up getting into their system and clogs up their digestive systems, and they end up dying. Obviously, this is some sort of a seabird. Maybe it died and it washed up on shore. Maybe it flew ashore and it ended up not surviving because of all of this plastic. Now, this guy has taken a scoop of water from the ocean, and that's what it looks like, right? So we've got all those plastic chunks that are floating in the water, but what we don't see are what are called microplastics. These are teeny tiny little pellets that are really hard to see, but they are also collecting in the ocean. Now, I've heard, and I don't recall if I've seen a picture of it, but apparently researchers have gone down to the bottom of the ocean in this area, and they see these massive mounds of microplastic, like underwater sand dunes almost, but they're not sand, it's plastic. Now, obviously, can't be good for our planet, right? And just chalk it up as one more thing humans are doing to hurt our planet. Okay, so that's it for this chapter. If you have any questions about things that we talked about or that I've talked about throughout the chapter, we'll have the Google Classroom. Ask a question on a forum on Google Classroom. Shoot me an email. Call me. Whatever you want to do. If you have questions, get a hold of me, and we'll have your test coming up here within the next couple of days. Hope you guys are all doing well, staying safe, and making good choices about who you're sharing your air with.